Hi, my name is Sydney Cumby, and this is my PHYS2212 Lab 2 Charge Tape Revisited. The purpose of this experiment is to further investigate the data obtained during Lab 1 by creating a more sophisticated computational model for calculating electric force in the charge on the charge tape. We will model the tape as a line of charges instead of a point charge to account for the distribution of charges along the tape. As shown in the main results of this experiment, there was the magnitude of the charge of one piece equal to 2.49 times 10 to the negative 8 coulombs, which was more than 2 times higher than the magnitude of the charge that was calculated using the point charge model in Lab 1. For models, we have the experimental and computational models. For the experimental model, it uses the same experiment and data as Lab 1. For the computational model, it models the tape as a line of charges to compute both electric force and charge. We assume that air resistance is negligible, and each U-tape has the same charge distributed throughout the tape. The fundamental principles used in this experiment are Coulomb's law, which computes the electric force of one charge onto another charged object. And since we are using distributed charges within Coulomb's law, we can also use the principle of E net is equal to the summation of EI. Gravitational force is also used to calculate the force upon the tape in the negative y direction. And finally, Newton's second law is used to tell us when momentum does not change, the net force of an object is zero. To recap the experimental model, our system was the U-tape and the surroundings were everything else within the environment, like the base tape and supports. The initial conditions were that the electric charge on the initial tape was zero. And for the process, it involved charging one U-tape with another piece of tape, and then which was held next to another charged U-tape which was sitting upon two blocks. Then we measured the distance of levitation between both charged U-tapes. The data that was gathered from the experiment is that the length of the U-tape was 0.2 meters, the width of the U-tape was 0.02 meters, and the distance calculated between both the tape A and tape B was 0.022 meters. From Lab 1, we were also able to calculate the magnitude of gravitational force on the tape, which was 1.00196 newtons, and the magnitude charge on a piece of tape was 1.17 times 10 to the negative 8 coulombs. With this data, we were able to use it within our code to compute the Lab 2. Here is shown as my computational model, which contains some of the values I had obtained here. Some of these values include the charge on the piece of tape, which is given as equal magnitude of the electric force and gravitational force. The next part here is a function which helps compute the electric field, and then next after that is a function that creates a line of charges for our computational model. This top code here helps us divide our tape into finite pieces to calculate a point charge for each of those pieces. And then we next have scale factors for our electrical field, electrical force, and gravitational force. Here the top functions are used to create and calculate the electric field and electric force at a small finite piece of tape, which we have then created. And then we will have a function that will add those values onto the total to calculate the total electric force of the piece of tape. This is the output diagram for the code. Notice the magnitude of the electric force and the magnitude of the gravitational force are equal due to F net on the tape equaling 0. And lastly, the magnitude of the charge that is on the one piece of tape. Realistically, the computational model and real-life model experiment will still have some discrepancies. Gravitational force and electric force are not exactly equal in real life, and other forces are likely acting upon the charged tape. Dividing the tape into finite segments of point charges to determine the charge proved to be more accurate to real experimental conditions than the model that was treated the tape charge as a single charge. A few sources of error are the pieces of tape could have had different charges from one another, mishandlings of the tape could have resulted in charge discrepancies, and we also did not account for other forces from surroundings like air resistance. For the additional questions, I'll start with the what if. Well, in Lab 1, we treated the tapes as a point charge and got the charge to be 1.17 times 10 to the negative 8 coulombs. And in Lab 2, we treated the tape as a distribution of charges and got the charge as approximately 5 times 10 to the negative 8 coulombs. The charge calculated in this is more than double the charge in Lab 1, which highlights a significant difference in the calculation between the two models. And for why, Lab 1 treated these charges as if they were concentrated on one point, but really they're distributed across the whole pieces of tape. In Lab 2, this was accounted for by a line of charges and just the point charge. Therefore, Lab 2 calculations are more likely to be closer to the real-world value. For my conclusions, the breaking of the tape into smaller pieces was more accurate in computing the charges across the tape. And point charge models do not appropriately reflect the charge distribution on macro-scaled objects. Thank you and have a good day.